Hi everyone, my name is Batrisha Balkis binti Abdul Aziz and my team members are Nur Batrisha Aina binti Muhammad Nazri, Alif Fahmi bin Azhar and Lo Jia Cheng. We are from Chemical Engineering Department and from Group 28 want to present about our integrated design project entitled of Methanol Purification. Hi, I am Batrisha Balkis. First of all, let me brief to you guys about the introduction of methanol. Methanol is a compound with the formula CH3OH, which is a methyl group, and it also has another name, which is wood alcohol, because it was once mainly produced by wood's destructive distillation. The properties of methanol are light, volatile, colorless, and flammable liquid. Methanol is used to produce 1,000 of products that impact our everyday life, such as to run vehicles and cooking foods. For the current production and market analysis of methanol, the global methanol market size was estimated at USD 38.98 billion. The compound annual growth rate for the market methanol is expected to increase to 5% by the year of 2025. Most of the demand is driven by China as it uses methanol for a wide range of applications, for example as a fuel and as an olefin feedstock. Other than that, the global market of methanol is dominated by the Asia-Pacific region such as India, China, and Japan. China is accounted for more than 20 million metric tons of coating production, which is 30% of the global coating output of methanol. Next, we move to the selection of production capacity and instrument part. The proposed plan that we are expecting is it will have a production capacity of maximum 2,500 metric tons of methanol daily. Steam methane reforming based synthesis gas production is usually applied for methanol plant with maximum capacity up to 2,500 metric tons per day. This production capacity is chosen due to the positive outlook on the global consumption of methanol. These are 5 selected instruments that we choose for our plant production capacity.
Alright, thank you Bisha for the introduction of methanol. So hello, I'm Batrisha and I'll proceed with the part 2, which is the process flow diagram. So basically, the process flow starts when natural gas in S1 and water in S2 are being mixed by a mixer before being fed into the reforming reactor. The water is supplied into the heater to produce steam. The methane gas is mixed with the steam before transferred to the reforming reactor. Next, the mixture will flow into the reforming reactors and steam reforming occurs. The excess steam is then reacted with natural gas supplied from pipeline and react with excess steam to produce syngas. The process continues with the reaction of carbon dioxide gas and water to form carbon dioxide and hydrogen gas. The vapor stream are the output for the reforming reactor through S3 and will be transported into the condenser. In condenser, the produced syngas stream from S3 is then cooled down to remove 95% of the excess water through the bottom stream of the condenser. The remaining syngas in S5 is then fed into the methanol reactor. In methanol reactor, syngas reacts with hydrogen to form methanol. After the stream from the condenser is being condensed, the stream S5 will react in the methanol reactor where carbon monoxide and carbon dioxide undergoes hydrogenation process to form methanol together with undesired products. The products formed in methanol reactor R102 will flow into a condenser through S6 to cool the mixture down to saturation point of methanol. The mixture is then fed into syngas recovery unit. The mixture from condenser in S6 will be distilled in syngas recovery unit. The mixture from S7 in syngas recovery unit will be split into 2 streams by a splitter. The 10% of the carbon monoxide and hydrogen gas will be vaporized and are purged in S9, while the remaining mixture in S8 will flow into the compressor to be recycled back into the methanol purification unit for further purification. The bottom product in S10 of syngas recovery unit will become the inlet of methanol purification unit and is further purified. Next, from S10, the mixture of liquid methanol and water will be pumped into the methanol purification unit. At methanol purification unit, high purity of methanol of 0.96 mole fraction is then separated. Final product, which is the methanol, will be produced as the overhead product in S11. Meanwhile, the water as the bottom product is sent off to wastewater treatment plant in S12. Alright, so that is all from me for the process flow diagram. Now I will pass to Alifami to explain more in details about thermodynamics in part 3.
Hello, my name is Alifami bin Azhar, and for this part of the equilibrium plot function is used for the generation of the liquid equilibrium graph of the mixture in the methanol purification unit D103. The temperature used in the experiment is 50 Celsius, while we compare the data from Dortmund data bank, which is 50 Celsius. Meanwhile, the red color plot is the 45-degree line signifying the vapor phase, has the same composition as the liquid phase methanol, while the blue line is the relationship between the liquid and vapor phase of methanol. Next, this graph shows the PXY graph, which blue line shows the bubble point, while red line shows the dew point of methanol water binary system in D103. On the left, we have the exponential graph, and on the right, we have the graph from the Dortmund data bank. Next, we are required to generate the phase envelope for the mixture in the methanol purification unit. The input of the methanol purification unit D103, which is S10. As you can see, on the left one is the bubble point, and the right one is the table of dew point. In this table, we can see the mass fraction of S10, which have total of fraction 1. And the graph show the relationship between pressure versus temperature for stream 10 obtained from the software. Next, we are required to predict the composition of and the mole fraction of S3. The left picture gives the simulation of S3 passing to condenser, to separator, and to S4 vapor and S5 liquid. The inlet has the temperature of 700 Celsius and the pressure of 750 kilopascal. After being condensed in the condenser, S31 is at 31.60 Celsius and the same pressure, which is 750 kilopascal, with a vapor component of 0.8909. And then enter the separator and exit at S4 at 1 vapor fraction and 31.6 Celsius and 750 kilopascal. The table shows the mass flow of vapor and liquid phase. S5 contain 1 fraction of aqueous and the same temperature at 31.6 Celsius and the same pressure at 750 kilopascal. The S5 mass flow of the vapor and liquid phase is shown in the table.
Hi everyone, now I'm going to talk about part 4, which is the separation process. And for the sake of some of the words hidden behind the camera view, I'm going to turn off the camera. Now I'm going to talk about the methanol purification units. So there are 2 diagrams here. The left diagram is the diagram that is drawn by using microservicio, and the second diagram at the right is the pictures taken from experiment. From both of the diagrams, you can see that the input is stream 10 and the top output is stream 11 and the bottom output is stream 12. And in all the streams, they are both consisting of methanol and water. And what have we done in the separation process? The requirement is to produce the methanol distillate of 95% purity. And the next one, we assume the suitable reflux ratio for the methanol purification unit, and we calculate the number of stages for the unit. From the manual calculations, we have calculated that the minimum reflux ratio is 0.1287, and from there we can see that there are several trials. Those 4 trials are according to John Copley's, which is we follow the range of reflux ratio, which is between 1.2 and 1.5 multiplied by the minimum reflux ratio. And we have calculated the R value, and after we have that R value, we proceed with plotting the graph of YA and XA to determine the number of stages required for the methanol purification unit by using Mercatili method. Next, we have also plotted the graph of trial 4. From the manual calculations, we calculate the equations of the equilibrium lines and the points. So the orange color line is the equilibrium line, and we have also drawn a 45-degree line from end to end of the equilibrium line. And we also calculated the Q line equations, and we plot the Q line into the graph. And from the graph, we can see that the Q line is intersecting with 45-degree line. The intersection point is showing the mole fractions of the methanol in the feed stage. Next one, we calculate the enriching line equations and we plot the enriching line. And then the enriching line starts at XD, which is the mole fraction of methanol at the distillate stage, which is at stream 11, and we stop the line at the Q line, so it forms intersections between the enriching line and the Q line. And we connect the intersections of the enriching line with XB. XB is the mole fractions of methanol at the bottom stage, which is at stream 11. And then we determine the number of stages by drawing the yellow color line, the yellow color stages, to determine the number of stages. When the graph of XA versus YA are plotted for 4 trials, we can see that the number of theoretical stages of the 4th trial is the smallest. So its reflux ratio of 0.1931 is being used for the optimum reflux ratio. Knowing the optimum reflux ratio is important because we can use it to determine the optimum conditions for the production of methanol and the number of the stages to be used for the methanol production unit. The number of stages is chosen to be at the minimum. It is because the lower the number of stages, the lower the cost and the lower the maintenance process. So that's all from me. Thank you very much.